wanted to solve this problem that involves a number of things from different classes over the semester. It involves momentum conservation. It involves kinematics, falling bodies, and it involves collisions. And all these things are wrapped up together in this little problem. So we're told that a bullet strikes a block that is resting on the edge of a tabletop. And the bullet and the block stick together, and the bullet block system fall off the tabletop and hit the ground a certain distance from the tabletop. And so I pictured that in this little sketch I made here. Over here on the left, this is the bullet. It's traveling towards the block. It strikes the block on the edge of the table and is embedded in the block on the edge of the table. And then the bullet in the block fall off the table and strike the floor some distance from the table. And we're given some numbers. We're told the bullet's mass, 8 grams. The block's mass, 240 grams. The height of the table, 1 meter. The distance horizontally the block lands from the table, 2 meters. And we're asked the bullet's initial speed. So I could add those quantities to the picture to kind of quantify the picture. So let me call the bullet object number 1. Its mass is 8 grams. The block's mass, I'll call it object number 2, is 240 grams. And then the vertical height of the table, that's 1 meter. I'll call that y minus y naught. That's 1 meter. And the horizontal distance traveled, I'll call that x minus x naught. That's 2 meters. And we've got to put this information together to find the unknown's initial speed of the bullet. And I'll call that V1. And so that's the information we're given. That's what we want to figure out. And we're going to do it through a series of steps. The first step is actually kinematics of falling bodies. And we're going to find the speed of the block with the bullet stuck in it as it leaves the edge of the table by kinematics. And then the second step, once we know the speed of the block with the bullet stuck in it at the top edge of the table, we'll apply momentum conservation to the collision of the bullet with the block to find the initial speed of the bullet. So we've got 2 parts to this, basically. 1, kinematics, and 2, collision. So let's go through these 2 parts. To find the speed of the bullet block system at the top of the table, I actually first found the time that it took the bullet and block to hit the ground, and then I was able to find the speed that the bullet and block were traveling at. So let's find that time to fall to the ground first. I did that by thinking about, by analyzing the vertical motion and using this equation of motion that describes the vertical motion. So it relates the distance traveled to the initial velocity, to the acceleration, and the time taken. And we're going to solve it for the time taken. Now, in our case, the initial vertical velocity of the bullet in the block is 0. So that piece goes away, and it becomes a simple equation for the time. The time is going to be the following. I'm going to multiply the left and right side by 2, divide by the acceleration of gravity in the vertical direction. And I'm going to take the square root, and that will give me the time. And if I put in the numbers into this, I've got 2 times 1 meter, so that'll be 2 meters in the numerator here, divided by 9.8 meters per second. And I calculated that, and it was 0.45 seconds. So that's the time to fall from the vertical motion. Now we can find the speed from the horizontal motion. So now let's consider the horizontal motion, and I'm going to write down the same equation actually, but for the horizontal motion of the block in the bullet. So it's the same basic equation, but with horizontal quantities. But this time, there is initial velocity. It's that velocity we want to figure out. But there's no acceleration horizontally. So the second piece on the right-hand side vanishes. And so if we want to find that initial velocity of the bullet plus the block, we just need to divide the left and right by the time, and substitute in the horizontal distance traveled, this time 2 meters, the time taken 0.45 seconds, and if you divide 2 by 0.45, I got roughly 4.4 meters per second. And so that's the horizontal velocity of the bullet block system, that moment that the bullet has been embedded in the block. Okay, now we can think about the collision between the bullet and the block that produced the bullet block system. So it's a perfectly inelastic head-on collision. And by thinking about that collision and momentum in that collision, we can solve for the initial velocity of the bullet. So let me sketch out the collision of sort of before and after picture of the collision. Before, we've got a moving bullet, M1, striking a stationary block, M2. And after, we've got a moving block M bullet. I'm drawing the bullet inside the block now. So here the mass is M1 plus M2. And this velocity, the final velocity after the collision, is actually the result from the first part, the kinematics part of the problem. So that we just found to be 4.4 meters per second. So to this arrangement, I'm going to apply momentum conservation. We solve this over here. So the momentum before the collision equals the momentum after the collision. Pi equals Pf. Now, momentum is a vector, but in this case, I'm just considering the momentum in the horizontal direction, or the actions in the horizontal direction. So I've just written a Pi and a Pf. I could have written a Pix and a Pfx. the momentum before the collision, well, there's the momentum of the bullet, m1 v1, plus the momentum of the block, but the block's stationary. So that's actually 0. And the momentum after the collision is the momentum of the bullet block system, which is their total mass, m1 plus m2, times that final velocity. And if you look at that equation, well, you know the masses, you know the final velocity. The only quantity you don't know is v1. And you can rearrange this straightforwardly for v1 by just dividing by the mass of the bullet. And you get this little equation here. And now all we have to do is to fill in the masses. The bullet was 8 grams, the block was 240 grams, so that's 248 grams total mass over 8 grams, and multiply by the 4.4 meters per second. And if you do this calculation, you get the bullet's velocity is about 137 meters per second. It's much larger than the block in the bullet's velocity because the bullet is much lighter than the bullet in the block system. And so to conserve momentum, the very light bullet must be traveling very fast compared to the much heavier bullet and block system, which is traveling comparatively slowly. So that's an interesting example because it really puts together so many different topics from this semester, from kinematics and falling bodies. Those were great discoveries about the influence of gravity on Earth, to our understanding of collisions and conserved quantities in collisions. In this case, momentum is the conserved quantity, and kinetic energy actually wasn't conserved. It was dissipated in the bullet striking the block and doing some damage and making some noise and heating up the block and bullet system. At that moment, when the bullet struck the block, there were forces acting. And those forces were responsible for transferring energy, transferring momentum, i.e. giving an impulse to the block and doing work on the block. And so it's really a problem that I think is nice in covering so much of the territory that we walked through over the semester. So that's one of the reasons I like this, enjoy this problem.